Here is a mark scheme for the 2019 Year 11 mock exam in physics. It's a 90-minute paper. Hopefully we'll do it a lot quicker than that. Now we're going to jump straight into question 1, and we're going to talk through the answers. So we're talking about a beaker of water that's being heated over time. You'll see temperature in degrees C, you'll see time in minutes, and obviously what's happening here is you've got the temperature increasing of the beaker of water, and then it's starting to decrease until it hits an equilibrium, where all the heat that's being supplied to the beaker is escaping from the beaker, so that's why we're at an equilibrium. We might get to that question a little later on, but essentially to start with it talks about what's the temperature rise in the first 2.5 minutes. Well, 2.5 minutes is going to be somewhere around there, and that lines up very neatly with 30 degrees. However, don't forget that the temperature rise is the difference between 20 and 30, which is 10 degrees Celsius. Most people, if they've ever made an error, would have jumped in and just said it's 30 degrees. So it's going to be 30 minus 20, giving us 10 degrees. Fairly straightforward if you realised that this was not starting from 0, 0. Next part, it says the beaker contains water of mass 60 grams, and it has got a specific heat capacity of 2.5 joules per gram per degree. See, now some of you might go, hold on, that 2.5 looks odd. Sorry, 4.2. What am I talking about? 4.2 looks odd because water should be 4,200. Yes, but that's 4,200 joules per kilogram. This is per gram. So if you see the gram and the grams there are lined up, so this question should be fairly straightforward. If you can remember, the equation for the energy is going to be M, mass times specific heat capacity times change in temperature, which is going to be 60 grams by 4.2 by, and the change in temperature from the previous question was 10 degrees. And if we pull that together, I think we get something like 2520 joules. But of course, we've only got two significant figures in each of those, so really our answer should be 2500 joules. But you get a mark for either of those, depending on how accurate you have been. The next question then talks about sketching a line on the graph to show the variation in temperature with time when a lid is placed on the beaker. Now, if I just do a little bit of a little diagram here, if we've got a lid on the beaker, then what's happening is that's preventing water molecules from evaporating out of the top, because now I've got a lid on the beaker. So it means that heat's going to be retained, which means that it's going to reach a higher temperature, so at equilibrium, and also it will mean that we are probably going to get a quicker increase in temperature. So there's the theory. So how does that relate? How would that look on the graph? Well, those two ideas we're going to draw in red. I'm going to look for a quicker increase and a higher equilibrium. So let's say a higher equilibrium, something notable is going to be something like that. And I think it's going to increase its speed temperature faster before it reaches equilibrium. So I think that's better. Okay, and why is that? It then asks, why is that the case? Well, I think that's because we can say that evaporation is prevented, so a higher temperature is reached, or indeed that could be described as it's reducing convection currents. Only for one mark, so don't over-egg that one. Good, so that's my thinking of the answers. So let's just see what the real answers were. I brought them here. 10 degrees, So that's right. You've then got the equation here, delta. Well, interestingly here, I used that as delta theta, the change in temperature, and I said the energy. Otherwise, the equation holds true. And then, yes, we allowed either 2,520 or 2,500 was correct. The line was a similar shape, starts at the same point and finishes above the pre-existing point, yes. And we allowed convection or evaporation is reduced, but actually that is a much better wording than the one I used. So I'm going to rewrite that in. The transfer of heat to the surroundings is reduced. So let's just write that one in, because that's important. So let's say transfer of heat to surroundings is reduced. All right, we're going to look at the next question, which is looking at the expansion of the universe. We have been given here two spectra from something which is a distant galaxy and something which you'd see on Earth, the laboratory frame of reference. And we see these distinct lines which are in the same patterns as the one from the distant galaxies to that which is in the laboratory frame reference. But the difference here, of course, is that we have a shift, and we have a shift towards the wavelength has increased than it has in the previous one. So we call this, of course, red shift, which you're all well aware of. So the question asks, we have one of the lines is sitting at 510 nanometers. The same line of the laboratory frame is 490 nanometers, so therefore calculate the velocity. So hopefully you would be able to recall from memory the equation which says that the velocity divided by the speed of light is equal to the galaxy wavelength minus the laboratory frame divided by the laboratory frame, which gives us 510 nanometers minus 490 nanometers divided by 490 nanometers. Now, because the nanometers are the same in each of them, you can forget about that. We could have, if we wanted, have changed this to 4.1 times 10 to the minus 9 meters. Very technically correct, changing everything into meters. But because meters is being used on all of these, nanometers is being used on all of these, then it's fine. It's just the ratio it's looking for between those. And of course, ultimately it's looking for the velocity. So first of all, we're going to work out what that fraction is, which comes out to be 0.0408. And of course, the final step, the velocity, is going to be 0.0408 multiplied by the speed of light. And that gives us 0.0408 by 3 times 10 to the 8, which is the speed of light. And that should give us, I'm just going to plug this into the calculator, and it comes out to be about 1.2 times 10 to the 7, 1.224, let's say, times 10 to the 7 meters per second. But it's asking for two significant figures as the last point, so that's 1.2 times 10 to the 7 meters per second is already given. It's quite interesting here as to which way round this ought to be. It's quite hard to know what lambda naught is as opposed to lambda. What I would say is that because whatever's happening at the top here must come out to be positive, so that's the way around to remember it. It's always going to be redshifted. Whatever, galaxies are expanding, it's not contracting. Most of the questions you'll be given. So therefore this must be a positive number, so make sure that you use the longer one first, shorter one, and obviously those two must be the same to give you the answer. Let's see if that is correct in the mark scheme for the first bit. Yes, we've got the correct equation, the rearrangement, the correct way round, and therefore answer with the correct significant figures. Excellent. Let's go back to the next question. our topic, and it's asking you to place the astronomical objects in the order of size. Straightforward if you memorised these respective sizes. Of course, this is going to be the largest, isn't it, the universe? That's a good way to start. And I think they've tried to be quite tricky here, because often you place the sun quite high up when you're building these systems, but actually the sun is the smallest. It is a star in these structures. Then around the star you have a solar system, and then many solar systems or make up the Milky Way. That's right. Many solar systems make up a galaxy, and of course Milky Way is a galaxy. Good. Hopefully that didn't catch many of you out if you'd done your revision. The next one asks about essentially a moon around Jupiter that's got an orbital velocity of, and it takes a certain time period. What's the radius? Well, this is really quite straightforward maths if you interpret this correctly. It's just it's understanding that the distance covered is the circumference of a circle, because the orbits are essentially circular. They are technically ellipses, but you can approximate that to being a circle. So the circumference of a circle, which is your distance, and the distance divided by time gives you the velocity. A very straightforward equation. So then what we're going to do is we're looking to calculate the radius, so we just need to rearrange to get radius. So therefore, radius is going to be the velocity times time divided by 2 pi. And some substitutions now required. Be careful about the units here. We've got kilometres per second, we've got days. That's what's going to trip people up. And it's asking for the answer in kilometres. So let's keep the kilometres in there, but let's convert everything else to seconds. So the velocity is going to be 8.204 kilometres per second. Do you know what? I'm actually just going to keep the units in to help. Multiply by that by the time period, t. That's 16.69. And this is days, so I'm going to times that by 24 hours in a day, 60 minutes in an hour, and 60 seconds in a minute. And then I'm going to divide that through by 2 pi. And that should give me my answer. So the next part of this question now talks about the evolution of a star. And we should be thinking about, when we're answering this question, the life cycle of a star. And so what I'm going to do is I'm going to bring up an image of the life cycle of a star. Well, actually two images, so we can remind ourselves of what's going on. Right, this is the first one, which talks about the different pathways which different stars take depending on the size of the star, massive stars versus small stars, and how they turn to a red giant, a small star like our sun, and that turns into a nebula and ultimately into a white dwarf. However, if something is a massive star, massive compared to the size of the sun, then that will turn to a supergiant red, and then to a supernova, which ends up at a neutron star or a black hole, depending on the size. So that's really what it's trying to reference here. So how I would answer that question would be, take note of the size of the star. So size star X is most likely to be our average star, because it's near that of the size of the sun, whereas star Y is going to be the massive star, 15 times larger than our sun, so it's going to be massive, and therefore it's most likely to end up in this state rather than that state. So how do we go about answering the question then? Well, I'm going to bullet point this because I think we're looking for 4 marks, so let's just bullet point this and explain what we're on about. We have star Y. It's going to burn brightly, and because it's burning brightly, it will use up its fuel more quickly, so it will be on the main sequence of its life for a shorter period. It will turn into a giant, a super giant red star, and then it will end as either a neutron star / black hole, whereas star X is similar to our Sun, so it will stay longer as a main sequence star. Sorry for the abbreviations, I'm trying to write fast. It will turn into a red giant, or a giant red star, and then it will end as a white dwarf. Okay, let's see what the mark scheme says. So the mark scheme says that the star will begin, it has low mass, so we reference the mass, but star Y has a higher mass. Yes, we reference the masses. Star X will stay in the main sequence line for longer than Y. Good, we've referenced that. It will become a red giant, but Y is a supergiant, yes. And one will finish as a white dwarf, the other one a neutron star and the black hole. Excellent. So that question is complete. Okay, moving on to the next one. A student has a small piece of steel, describe an experiment, you could find the density, and you made a diagram to help you. So you're going to remind yourself of what you did with this solids, liquids, gases topic here. Essentially what you need to work out is you need to work out the mass of the object and the volume of the object, because that will show you, that is going to give you the density as per the equation. I've written rho there, which is the symbol for density. So how do you work out the mass? How do you work out the volume? Well, it's a small piece of steel. It's likely to be regular in its size, so therefore you might measure the volume. And the mass is quite straightforward. However, if it's not regular in volume, then your best way of solving it is probably using a Eureka can, in which you have water that is filled to the point of this arm. You drop into it your object, and you would collect in a beaker or some other vessel the quantity of water that's being displaced. So this is the displaced water. And you would measure it. And it would either be a measuring cylinder, in which case 1 milliliter equals 1 centimeter cubed, or indeed you could weigh it as water. But let's keep to that idea, the idea that we will have a measuring cylinder. So that's how you're going to get the volume. Of course, I mentioned that it could be, if it was regular shaped, you could measure it, but this is the fail-safe way of doing it. This is using Eureka can. Yeah. Just write in what this is, the Eureka can. And then you're going to measure with scales the mass, or, well, technically the weight, but you're going to interpret that as a mass of the object. So some scales, and that's going to give you the mass, hopefully in kilograms. So we would write that out, that process out. So I'd write it out as bullet points, just to be efficient, but you probably ought to write it in open prose. So that would be that you would weigh the object to determine the mass. You would then place object in Eureka can to measure displaced volume of water. when you're describing experiments, and because you don't actually do a practical in the GCSE, but the practical is determined through through a question in the paper, all those practical skills that you would have honed over this time, you're going to need to try and reference in the practical, so you're showing you're good scientists. So I'm just trying to think here of practical problems that might have gone wrong, or ways in which you can make things more accurate. What you would probably do is you would probably repeat that the displacement, repeat the displacement, or the Yr11 step, let's call it. Three times. Find an average. In other words, this, of course, is it's unlikely that you're going to get the exact result three times. You're trying to make it more accurate, because also bearing in mind this is a small piece of steel, so it's not going to displace large amounts of water. Small bit of steel. What else do we do in order to try and make it more accurate? We'd probably need to say that we'd want a measuring can, a measuring cylinder, with 1 milliliter with 1 milliliter scale, because then we can be more accurate as well. Then once we've found the values, we then take the use the values for mass and volume in the equation, and I'll probably look that you've stated it, that density equals mass divided by volume. Now 5 marks, it's quite a lot. Let's see how many of those marks I would have got by having written that down. So it's asking for you to measure or find the mass using a balance, allow weighing with scales, so that was okay, we got that. Clear diagram marked, yes. Finding volume using a displacement method, good, that's what we said. Allow the correct formula for volume, i.e. object tied to a thread, awareness of the meniscus. Oh, so that's really useful, and a suitable experiment there. So I suppose this was as I described, the sort of the finesse part of the question. Object tied to a thread, so you're not dropping it in, so there's no splash. An awareness of the meniscus, that obviously means that the edges of the water, that's why I've actually drawn here the edges of the water here, moving up, that's the meniscus, to be aware of that, because if you read that wrong, you're meant to read level with the bottom of the meniscus. And then measure at eye level, so there's no parallax. Repeat the readings, which we did there. Take an average, which we said. Balance on a horizontal surface, good. Avoid splashing. So lots and lots of opportunities for you to gain these extra little marks. But I describe these as ways to finesse your answer. The bulk of the answer was achieved through this method, through the method marks here, MP 1 to 5. And these are the ways to finesse your answer, of which I got a couple of those rather than all of them. And then finally, of course, you need to have stated the equation which you have used as well. So one that to easily lose marks, but the one that you ought to just approach, as I suggest, is sort of scattergun, throw all the information you know down. So therefore you're going to pick up as many marks as is possible. Good. Okay, let's take a look at where we're headed next with the next one. Okay, a little bit of speed, distance, time here. Somebody's dropping a coin from a height, and then it shows you the velocity time graph, which you gained here, velocity time graph, which is nice and straight, which is excellent, because a straight line on a velocity time graph shows a constant acceleration. and this object will be accelerating according to gravity, which is constant. And then it asks us, state the equation linking acceleration and time. Okay, so acceleration, and I suggest you write out the equations rather than using symbols, because if you get the wrong symbols, then you're not going to get the marks. And lots of you might have written velocity divided by time. However, what I would suggest you write is the change in velocity divided by the time taken. So that's how we really finesse those answers. Change in velocity divided by time taken. Those, I think, are really important bits when you're talking about velocity. So it then says the coin hits the ground at a time of 0.62 seconds and a velocity of. Calculate the acceleration of the coin as it falls. Give the unit in your answer. Okay. What's important here is that it's starting from 0, 0. So when I am looking to substitute the values into the equation, the acceleration is going to be 6.1 meters per second minus 0, because it started from 0, and the time taken was 0.62 seconds. Critically important there. And the answer is 9.8387 if we're plugging into a calculator. And bearing in mind, to be absolutely proper, there's two significant figures, so our answer should only be to two significant figures. The acceleration 9.8, and hopefully you've remembered correctly that it should be meters per second squared. Good. State the feature on the graph that shows this acceleration. So what's the feature that shows the acceleration on a velocity time graph? Well, you should remember this, that is the gradient of the velocity time graph shows that feature. So let's just put that in. The gradient, one that I hope you all remembered. And calculate the height from which the coin was dropped. Use the graph to help you with your calculation. And again, as we would have remembered that the gradient is the acceleration, hopefully you should also know and have recalled that the area under the graph is the distance travelled. So the area is going to be a half times the base times the height. And we know that the base is 0.62 and we know the height is 6.1. We were told that. So if I then just substitute those values into my equation, that gives me the distance, which is the same as this case as the height, is a half times the base, which is the time taken, technically, times the height, which is the change in velocity, which gives me a half times 0.62 by 6.1, values taken from just up here. I'm just going to quickly plug that into the calculator and make sure I get the exact result. 0.5 by 0.62 by 6.1 gives us 1.891. Again, only two significant figures in all these things, so we could just leave that one out and leave it as 1.89 meters. Okay, trickier now. We are now dealing with a very large height, and the very large height is therefore now meaning that we're hitting the velocities high enough to have some air resistance. And so the air resistance will therefore cause a reduction in acceleration. Oh, and I'm already into the first question in some ways. So, explain why the velocity of the ball changes in this way refers to the idea about forces. So, let's just remind ourselves of what's happening at start, I'm going to draw the ball at different times, and then I'm going to draw the forces on there, because it's asking us to reference the forces, so that's really important. So let me draw in the forces. Now, it's dropping. No, that's right, it's dropping. So the force acting down in each case is the weight. So hopefully you're sort of now seeing that I'm drawing forces onto a velocity time graph. Anyway, it gets a bit complicated, but hopefully you'll be able to see what I'm doing here. And of course, initially, very slowly, the drag that's experienced on that ball is very small. As it gets a bit faster, of course, the drag starts to increase, until we reach a stage in which the drag is equal to the weight. And if I were to draw this in a yellow pen, hopefully you can see this, we've got quite a lot of, I'll call it our resultant force there. The resultant force is getting slightly smaller. The resultant force is pretty negligible, and then suddenly the resultant force is equal to 0. Which means that, if the resultant force equals ma, if I have no resultant force, I have no acceleration. If I have a high resultant force, then I have a high acceleration. And if I have a low resultant force, I have a low acceleration. So let's try and write that down. I'm going to bullet point it. We've got 5 marks to try and capture all those ideas. Written in prose would be better, but let's see how we get on. So, as the ball picks up speed, so it experiences drag. The resultant force on the ball reduces as the drag increases. This reduces the acceleration on the ball, and as acceleration is equal to the gradient of the velocity time graph reduces. Okay, so we sort of described the principles there. So really, what's happening towards the end point? Well, at the end point, this point right up at the top here, when the drag equals the weight, the resultant force is equal to 0. So then the acceleration equals 0. So then the object falls at a constant speed, which equals a terminal velocity. Okay, I think I've been pretty thorough there. Let's see how many of those marks I would have achieved. So, we have, first of all, we have acceleration is the change in velocity over the time taken. Good. And if you are using the symbols, then you needed to make sure it was the right symbols. You were given, in order to work out the acceleration, you needed to substitute into the equation. We did that. You needed to evaluate it and the correct units. Yes, we did that. We said it was the gradient as the acceleration. We said the height was the area under the line. So our half base height gave rise to the correct answer. Good, we're winning here. And you did have a range which it could fall in between. And then, for the last bit, which is the explanation bit. How many of these did I manage to get? So weight's acting on the ball, so it's accelerated. Drag is acting on the ball. The drag increases with the velocity or the speed. Eventually drag will equal to weight. There we go. Resultant force is 0. Has 0 acceleration, or a constant velocity allows reaching terminal velocity. So we pretty much captured everything. We gave a bit more detail actually than was needed. Superb, right? We're making good headway. Let's get to the next one. A bit of electronics. We have a circuit, and it asks us in this circuit, it's an incomplete circuit, and it's asking us to draw a thermistor to complete the circuit. Thermistors are always are always placed in series in a circuit. The way I remember a thermistor is a bit like a hockey stick through a resistor. It's dealing with temperatures, of course. Okay, so hopefully you knew the simple equation. Then add a voltmeter to the circuit in order to measure the voltage across the lamp. Okay, now voltmeters are always connected in parallel. So 1, you needed the connection in parallel, and 2, it needs to be across the lamp. Be sure that, rather than across the thermistor. I'm sure that's where the 2 marks have been given. Okay, hopefully you remembered that. That looks like a pretty standard circuit which you've drawn many times. The voltmeter uses a voltage of 5.6 volts. Good. The ammeter measures a current of. State the equation linking. Again, a recall question here. So we're saying the resistance is equal to the voltage divided by the current. And then it's asked you to calculate the resistance, which seems straightforward. But there's a few areas here that they might try and catch you out. One of them is that they're using milliamps, because that looks like a huge current, doesn't it? But it's actually in milliamps, so make sure you don't fall foul of that. Let's write down the equation. I'm using the symbol equation here. Hopefully you can see the similarities between these two. And the voltage is going to, so I've written out the equation, I'm going to substitute in the answers. And the way I convert milli into normal amps is I know it's 1,000th, so I just divide that number by 1,000. I don't try and guess at how many decimal places I need to move it, and that will come out as 0.97 amps. So then I substitute that in, make sure I'm typing it in correctly into the calculator, and that gives me an answer of 7.0886 ohms. It's already given. So because I've got everything to about, well, maybe 3 significant figures up here. No, 2 significant figures. I'll leave that as 2 significant figures, so I'm going to leave it as 7.1 ohms. Good. So now it says the complete circuit is moved from a cold room to a hot room. Explain how that would affect the brightness of the lamp. Let's remind ourselves of the circuit. So what's going to happen? There's only 2 components here, and you need to hopefully you can recall that with a thermistor, and most thermistors behave in this way. I know that you can get 2 types, so you might find in a textbook, you go, oh look, it's actually, you've got it wrong, sir, it's saying the other thing. But most of our thermistors we're dealing with, that as the temperature increases, the resistance decreases. I always think a bit about it as if you're putting energy into the system, increasing the temperature, then the resistance drops. That's just the way I memorise it. So what would happen, therefore? The overall circuit has got a reduction in resistance. And that means if the resistance goes down, then the current is going to go up for the same voltage, which is constant. So if I increase the temperature, the resistance comes down, the current goes up, and so the brightness will go up. And of course, vice versa to all of that. So let's explain how to affect the brightness of the lamp. Well, if the temperature increases, the resistance of thermistor decreases. Yeah. So the overall resistance of circuit decreases. So for the same voltage, the current increases, and so therefore the brightness of bulb increases. Okay. The next bit then asks for, state how the current in the circuit would change if another lamp is added in series to the first one. Well, can we go back to the circuit? If we were to add another bulb in, let's say here, in series, then the overall resistance of the circuit increases. If the resistance of the circuit increases for any given temperature, then the current will decrease. And if the current decreases, the brightness decreases. So let's go back and let's say it's only 1 mark, so we can be quite quick. So we can say that there's an increase in overall resistance, so the bulb decreases brightness. Okay, let's see how successful we've been with the mark scheme. So right from the start we had a correct thermistor. It doesn't matter which way up that is, but that's still correct. And they even reference there like a hockey stick. The correct symbol of the voltmeter, we've got it connected in parallel with any component, but if it's connecting component with the lamp, then you get the second mark there. We were right with the equation, which is excellent. Dimensionally correct substitution rearrangement of valuing, giving us to 7.1, yes, because we had obviously rearrangement substitution. And interestingly there, it did say, of course, remove 1 if you didn't get the milliamps to the amps. And it's allowed quite a lot of different values in there. But try and make sure you round it to the right number of significant figures. Okay, as it's the brightness increases, as we said it would, because the thermistor resistance decreases and therefore the current increases. We got all of those. And the voltage of the lamp, or indeed, yeah, it could have been, we could talk about it in terms of voltage of the lamp. So that's one we missed out, but one that would be credited. And indeed, the current decreases for an equivalent reason of any of those of the above. Okay, good. So, back to a quick question on radioactivity. We have Americanium 241, and it's used in smoke detectors. How many protons are there? Well, protons are the numbers at the bottom. So the answer is A. Simple as that. No argument about it. Number of neutrons, however, is going to be 241 protons and neutrons minus 95. Number of protons, it's the difference between those two values, which gives us, I'm just going to type it in to make absolutely sure, 146. Good. It then asks how many electrons are there in a neutral, and the key here is neutral. If it's neutral, the number of protons must be equal to the number of electrons in order for it to be neutral. So therefore it's going to be 95. It's the same number again. It's a fast and furious question. Hopefully you got that all correct. And then it says, when it decays into an alpha particle to form Neptunian 237. It's given you the symbol for Neptunian, it's put in the 237, but complete the nuclear equation. So what you need to recall is an alpha particle is a helium nucleus, and helium has 2 protons and 2 neutrons, giving you 4 particles in the nucleus. Then you need to know that these have to add up to be equal. It's just like a very simple equation. So that must be 93. Good. The next part says, after the decay, the Neptunian emits a gamma radiation. State what happens to the number of protons and neutrons as a result of the gamma emission. Well, there is no change in the number of protons and neutrons because gamma is an electromagnetic wave. And that's why it's written in this form. It's written as 0, 0 because it's gamma. And it doesn't have any protons, nor does it have any neutrons, so both are 0. So therefore, if we did have Neptunian 93 going towards gamma, whatever's left is still going to be Neptunian 93, but just with less energy, because gamma has taken the energy away. Okay, now here is our smoke alarm. I described that it was used as a smoke alarm. And this is what happens in our homes all the time. If you've ever taken a smoke alarm down, the older version with the batteries in, you'll see it says it has a radioactive warning sign on it. And we have a plastic case. This is the circuitry. We have an alpha detector and the alpha itself. And every time that the alpha is emitted from Americanium and it comes across, this detects it. However, if something were to get in the way of alpha, which alpha can only penetrate a couple of centimetres of air, but if a big smoke particle gets in the way, it won't get across, this doesn't detect it, and the alarm goes off. So in normal operation, the count rate measured is 100 counts per second. If the count rate falls between 80, the sound alarm explain how the rising smoke caused the... Good, so that's what I've done. So another bullet point, alpha particles cannot penetrate smoke. If smoke were to get into the alarm, the detector would see a count rate lower than 80, and the alarm would sound. Okay, good. So now we're doing a little bit more maths in this. It's saying Americanium has a half-life of 430 years. Describe what is meant by the term half-life. So this is a definition learned. This is the time taken for the number of radioactive nuclei or the radioactive particles emitted to reduce to half their value. Good, and I'm just wondering there, because it's 2 marks, is there any little finessing thing that I'm missing which might be offered up as a mark? I think what would be useful there is to write it's the average time taken, because it's really hard to deal with radioactive decay to be precise with it. You're more likely to be taking numerous attempts at half-life and then averaging them to try and find the best predictor of the real value. So average time taken, I think, is powerful, and that's probably going to get us our 2 marks there. Okay, then it says Americanium 242 has a half-life of 16 hours and is a beta emitter. Explain why Americanium is not suitable for a smoke detector. Well, beta particles can travel through smoke. So there won't be a reduction in the count rate when smoke rises. So that's not very good because you want the alarm to go off. And number two, 16 hours as a half-life. That means you'd have to be constantly replacing the radioactive source. So you would need to replace the radioactive source. Regularly. And you don't get radioactive sources like you do batteries. You can't just plug in a new radioactive source. So you'd need to replace the entire thing on a very regular basis. So that's another reason why it would not work very well. And I'm just thinking for the 3 marks, is there anything else that we're missing from them? No, I think we've covered the major items. So let's see what the mark scheme says in that case. Jump across. So we've got the first part of this, which was the diagram and the... Here we are, sorry, let's wrap here. So 95, we've got that. B, the number of neutrons, check. C, yes. D, yes. We've got the answer to B correct. We've got the answer to number 3 correct. And then, coming down here, we've got the right answers to those 3. These were all quick recalls, so hopefully there's no debate about these. We also said for a gamma that the number of neutrons doesn't change and the number of protons doesn't change. You could have achieved it with just saying nothing changes, but we were just saying that no protons and neutrons change. For part C, so it's the same. This is the same. Sorry for any confusion there. For part D, it says, explain how it works. Smoke absorbs the alpha particles. Less alpha particles reach the detector. And also you say it cannot penetrate smoke, so we got that bit correct. So we're doing well so far. Well done, me. And then it says time taken. So remember I said average time taken. But it's important here that it's the time taken for radioactivity to half or the number of nucleons to half. So we did talk about either of those in our explanation. But it's interesting what it says, reject half the time. That's quite interesting. And it rejects the idea of particles, molecules, breakdowns, or reactivity, the nucleus. It wants you to be precise. So it wants you to be precise about the radioactive nuclei, all the atoms, or the isotopes to decay. Now, was I precise enough there? Let me just take a look. Yeah, I said radioactive nuclei, so I was okay there. But that's interesting to be... Or the radioactive particles. That's probably a bit loose. That probably would not have got the marks, that one, if I just left radioactive particles. I ought to have said there, if I wanted to say radioactive particles, I ought to have probably said the radioactivity to... No, it doesn't actually state it there, but anyway, precision, that's the key, that's the takeaway. Be precise about that. Okay, now there were 3 marks in the last one. I wondered whether I got all 3 marks. I wondered whether I'd written enough for 3 marks, but let's see whether it would. Beta would penetrate the casing. That's the one I didn't get. I did say that the beta would be pulled by the smoke, and also I said that you'd need to replace it frequency. But what I didn't say was the beta would penetrate the casing, which is a health hazard. So that's important. And also the last one, I didn't put down there that the alarm would trigger due to naturally decreasing count rate, because of course all sources naturally decrease. So that's really interesting there. So -1 for Mr. King on the overall score so far, but that's the one I missed, which I think is important there, the hazardous to health. Even though hopefully it will be on the roof of your room, but still that can get through. Okay, so 1 mark down for me so far. Good, let's get to question 8. Okay, so this question is a bit of a combined one on moments and magnetic fields equally. What we have here is the pivot, a weight, and a coil of wire that will create an electromagnet, which will cause a force on the permanent magnet in order to create a force on this side. So it is a seesaw. It's just an elaborate way this way is constructed. The student's method is to look at the strength of the magnetic field of the current carrying coil as you change the current. Interesting. So they attach a small magnet to one wooden rod, place on the pivot at 8 centimeters, attach the weight to the other side, a known weight, and then work out the current needed in order to balance that weight out. So a weight of 0.1 is needed to balance the rod when the current is 0. Interesting. So 0.1 Newton needed just to set it balanced. Right. Calculate the weight of the magnet. Ignore the weight of the holder. Oh, I see. Okay then. So, what do we have? We have bear in mind, the clockwise moments must equal the anti-clockwise moments. Clockwise moments must equal the anti-clockwise moments. And a moment is going to be the force times by the distance. So, simply, we have the weight of the magnet multiplied by 8 centimeters is going to be equal to 0.1 Newton multiplied by 20 centimeters. Now, nominally, we would be converting this into meters, but because it's centimeters on both sides, it's not a problem. So let me quickly rearrange that and say W, the weight of the magnet, is 0.1 by 20 divided by 8, which gives us 0.25 newtons. I think that's right, yeah. That's 2 over, or 1 over 0.25 newtons. Okay, good. So then, the student increases the current to observe that the rod rotates anti-clockwise and the magnet moves towards the coil. Explain the observation. Well, if you increase the current, that will increase the force between, or it creates, should I say, creates a force between permanent magnet and coil of wire. And why is that? Because the coil is becoming an electromagnet. The bit that I think is quite interesting here is that it says the student increases the current and observes that the rod rotates anti-clockwise, yes, and the magnet moves towards the coil. Okay, sorry, I was thinking about it was going to reference a Newton's third law thing. No, so we've got all that we need here. So we're increasing the current, and that creates a force between the permanent magnet and the coil of wire, because the coil is becoming an electromagnet and therefore attracting it, and therefore that increases the anti-clockwise moment, so the rod rotates. It's important to put the last one in, often forgotten, this last point here, because you're trying to explain it, but you're explaining it and the consequence is what you then observe. Okay, and then we have some results. Again, I mentioned here that the practical aspect is not being done through an exam or through coursework, it's being done through the paper. So here you yourselves will have to be doing what you might do in that sense in the exam. And it'll ask you to, you've got some current, you've got weights needed, plot the graph using the independent variable on the x-axis and the line of best fit. So the independent is going to be what you change. This is what we changed, and this is what we measured. In other words, this is the dependent, and this is the independent. Independent always on the x, which it tells you, and dependent always on the y. So I have, I'm just going to plot this very quickly, I have 1, 2, 3, 4, 5 points there, and I need to move to something like 4.5, let's say 5, vertically, and I need to move to at least 1.2, so I've got 1, 2, 3, 4, 5, 6, 5, so let's take, this is 0.2, 0.4, 0.6, 0.8, 1.0, and 1.2, and that axis is going to be the current in amps. The vertical one is going to be the weight in newtons, and I'm going to have to go to 5. So I said this was this was going to be 1.0, 2.0, 3.0, 4.0, oops, 5.0. And then I need to plot. So I have 0 and at 0, weight needed was 0.1, which is there. I'll plot this in blue actually. Then at 0. Let's shrink that a little bit. 0.1, I have 0.5. 0.1, 0.5. 0.5, which is here, I'm looking at 2.1, 0.7, I'm looking at 2.5, okay, and then I'm looking at 0.9, 3.7 there, and 1.1, sorry, 1.1, looking at 4.5. So it's not a wonderful straight line, but it's not bad. And what I'm going to try and do is try and draw as straight a line as possible on there. So it's just, I'm not going through the axis, and I think that's important. I want as many above the line as below the line. So I think something like that is probably my best bet. Okay, let's see what it's asking me to do with that data. It suggests why the student should repeat the reading for 0.7 amps. Well, 0.7, well, that's really, that's even more interesting. If I were to draw in my line, ignoring that, maybe some of you did this, if I were to ignore 0.7, then actually they will fit fairly well on a straight line. So what we'd say is there's an anomaly there. So that's useful to know. So it doesn't fit on the straight line. The value for 0.7 doesn't fit on the straight line. So it could be an anomaly. Repeat to check. Describe the relationship between the current and the force produced by the magnetic field. Now, ordinarily I would say it looks directly proportional. I dot E, the way you describe it, it's a straight line through the origin, but it's not through the origin. That's how I describe what directly proportional is, but it's not through the origin. So how I describe it is, I'd say it's proportional. Or I would say that the current is proportional to the weight. And then finally it asks that it estimate the weight needed to balance the rod when the current is 2 amps. So let's place in 2 amps. Interesting. We don't have anywhere near the current for 2 amps. It's well beyond what we've got here. So we need to sort of extrapolate and keep going out and then seeing what it's likely to be. So what we can say is that the gradient, or how does it look as though it's behaving? Let me just look roughly at how it's behaving. It will be, I can draw this in a different colour if I can. We have approximately, most of these things are sitting on the straight line, so this triangle here is going to be 1.1 and 4.5. 1.1 and 4.5. So my gradient equals rise over the run, which is 4.5 over 1.1. When I plug that in to my calculator, it gives me 4.09. Let's then take that back. And it also says estimate. Sorry, I was going for real precision here, but estimate. But let me just show you what I'm trying to do. 4.5. So what we're saying is that we take if we were to take the current and, we were to take the current and multiply it by 4.1, that should give us the weight. So if I were to look for 2 amps, then it's going to be 4.1 times 2. I'm going to say the weight is about 8.2 newtons, which is approximately 8 newtons. That looks like a very mathematical and a difficult way to do it, but what I think it's roughly saying is, well, if 1 amp is about 4.5, roughly, then 2 amps is going to be somewhere around 9-ish. Or indeed, if 1 amp is somewhere between those two, so 1 amp is going to be somewhere between those two, which is about, what's that, about 4-ish. Then 2 amps is going to be something like 8-ish. If I haven't made that too complicated. It's an estimation. About 8. Okay, now I just realised, going back, that I have made an error right at the start of this, so I just want to take you back. An easy error to make, brain's getting tired, in that here, and I'm sure you would have picked this up earlier as well, in that I thought that 20 centimetres was what was represented between there and there, but it's not, of course. It's saying 20 is right to the end. So this length here is 20 minus 8, which is in effect 12 centimetres. So when I've done my calculations, I should really have here 20 minus 8, which gives my answer as 0.15 newtons. Okay, some of us might have made that error themselves, so you're in good company if that's the case. But luckily it didn't have to carry on. So let's just jump straight to the mark scheme and see how I've got on with the answers to that part. So we did the correct evaluation, finally, and we got to 0.15 newtons. And it says that if you did what I did, you only get 2 marks. So they realised that's something which they tried to trick people, and I fell for it. Okay, for part B, it then describes the coil becomes an electromagnet, which we mentioned, and that produces a magnetic field. We didn't say magnetic field, but we said it attracts or exerts a force. And then we referenced that it's the anti-clockwise moment. And that's important there because what was the consequence of it? It also then says allow current for court, reject if repulsion mentioned, allowing creating additional anti-clockwise moments. Yeah, I suppose because it tells you which way it's going, you know it's attracted, it can't be rejected, it can't be repulsed if they've said it's increased the anti-clockwise moment, so they're defining which way it's being dealt with. Good, it then describes that you have a sensible scale, which we did. It occupies over 50% of the grid, it did. We correctly label the axis with units, importantly. The units in there. The correct orientation, it had to be current and it had to be weight added. And then the points would correctly placed in. Straight line avoiding the anomalous reading, which I realised later on what he was after. And then it suggested, as I was expecting it to check the accuracy and validity of the readings, because it appears anomalous, so that's why it looks a bit odd. And then, now this is the bit I said, it looks like it's directly proportional. Well, yeah, that's why they've put it in brackets then. But they're sort of saying, as current increases, the force increases, and a suitable comment about linearity. Okay, so they're being quite liberal with that. But again, we would have got all the marks there. And then relevant use of one of the data sets to get to 8.1 newtons. So, yeah, so they were looking for something quite precise there. So I wasn't far off doing what I was doing. So they wouldn't get around, you wouldn't get away with just doing 8, you had to get to 8.1. So probably best, not a small task, I mean, they've asked quite a bit there, I think, of your general maths knowledge. So that takes us up to question 9. So here we go with question 9. It's talking about ball A and ball B making a collision with each other. We're talking about momentum here. They're identical size balls, so we need to talk about, first of all, what's the principle of conservation of momentum. So essentially it means that the momentum before a collision equals the momentum after a collision. And then if there are no external forces. That's the bit which is really, really useful to get in and which most questions will look for. So I'll be interested to see what they're looking for if they're only offering 1 mark, but do always remember it so you can write it in. And then it talks about here, ball A, these are similar size mass balls, 0.16 kilograms each, and then afterwards this moves away at 8 meters per second, and it's asking what will the speed of the other ball be moving at. So let me just redraw that. If this is a before picture, then the after picture is going to be post collision. You've got ball A going at velocity v and ball B going at 8 meters per second. So what I always like to do with these calculations is write down the momentum, I hope you know that P is momentum before a collision, must equal momentum after a collision. And the momentum before the collision is going to be the mass times the velocity, and that's going to be the mass of A times the velocity, and afterwards mass A times the new velocity, dash, let's call it dash, plus mass of B multiplied by 8 meters, by the 8 meters per second. So let's, rather than me write it all algebraically, let me write in there 10, because it's the mass times 10. And indeed, let me write in the mass of those 3, which I know, which is 0.16 multiplied by 0.16 and 0.16, make sure that's a plus sign in there. And what we're looking for is V, so let's rearrange to find V. This is going to be 1.6 minus 0.16 times 8. I'm just moving 1 to the other side, 0.16 v dash. And so therefore v dash is going to be 1.6 minus 0.16 times 8 divided by 0.16 and gives us 2 meters per second. And I can jump to 2 knowing that really well, because I think most of you intuitively would have got this, because you know that because of the same mass, it would be wrong to write this down because it's physics. This is not right. It's not just 10 minus 8 equals 2, and we can't really give that marks. But intuitively you know that it's going to be whatever the difference is because the masses are the same. But you do need to go through that entire explanation in order to probably get the 3 marks that they're looking for. So let's just look at the mark scheme and see what it's after. The total momentum before the collision equals total momentum after. They're not interested in the external forces bit, but do remember that ignore unqualified momentum is conserved. So anything that's just unqualified, they have not given marks to, interestingly. The next bit, it wanted you to work out the momentum before and then to work out the momentum afterwards in that algebraic format and then come up with the answer. So we did well there. It's better than the last question. Good, let's go straight to 10, making headway. The question is about electromagnetic waves. Which of these are used by mobile phones to send? You either know this or you don't know this. It's microwaves. Which of these is harmful? Effect of infrared. Infrared is like the oven or the toaster, so it's going to cause heat. It can cause, it's not internal heating of the body, it's not blindness, so this is UV often, this is micro, skin burns, cancer is gamma, and so it's going to be C, it's burns. Burns as you or I know about them, not radioactive radiation burns. Optical fibres can use visible light to send information. Which one of these in waves has a higher frequency than visible light? Again, you either know it or you don't know it. Higher frequency, shorter wavelength than visible light. The other one is ultraviolet. State the equation linking speed, frequency, and wavelength. If you're not happy with those symbols, then do write it out. Velocity or speed is frequency times wavelength. And then it's asking you, fairly straightforward, to calculate the wavelength of visible light in the optic fibre. So you're looking for the wavelength, which is going to be velocity divided by the frequency. This requires careful plugging into your calculators. And divide that by 4.5 times 10 to the 14. For those of you that feel more competent with maths, you know that's 2 times 10 to the 8 over 4.5 times 10 to the 14. And so that's going to give us something in the order of, I'm hoping my scientific calculator is going to do this, gives me 4.4 times 10 to the minus 7 meters. The calculator should have produced that for you. Good, straightforward question, getting lots of marks there hopefully. Okay, now we're on to one with forces. We have a trolley that's linked to a pulley and mass is on the pulley for it to drop a distance. This is a resultant force, and that's going to cause a resultant acceleration on the trolley. So let's see what it said. State the equation linking the unbalanced force, the mass and the acceleration. Hopefully you all did your revision, and you worked out, and you knew that it was that F equals ma, or the resultant force equals ma. Calculate the unbalanced force on the trolley. So we have 5 kilograms. That's not a force, that's a mass. So what is the force going to be? Well, we've been given some values here which we can work with. So these values above here we need to make use of. So the F resultant, or the unbalance, is going to be the mass times by the acceleration, which is 0.87 by 7.9 meters per second squared. If I plug those into the calculator, giving us 6.873 newtons. Now, how many significant figures? 2 significant figures is probably best, so it should really be about 6.9, because I've got 2 significant figures on there, on both sides, so 6.9 only, a bit of a rounding that goes on there. What is the direction of the frictional force acting on the trolley? Well, it opposes the motion. So I would say to the left. If the trolley's moving to the right, it's to the left. And where do the 2 places where the trolley friction occurs? Well, that's between the trolley and the table, and also between the pulley and the rope. Good. State the equation linking the gravitation, again, one that you just hopefully remember, GPE equals mgh. Or should I say the change in GP is mg delta h, the change in it. So calculate the change in when the 5 kilogram mass falls. Well, when we look at it falling, we know that it's falling 0.65 meters to the ground. So therefore, 0.65 meters, let's jump back to show my values here. The change in GPE is going to be equal to 5 times 10, it's given, by 0.65 meters. And what does that come out with? I think it's, I'll double check, 32.5 I believe. Yeah, 32.5 joules. But again, everything seems to be given in about 2 significant figures, so possibly, I wouldn't blame if you wrote down 33 joules there. And then it says, this one here, state the kinetic energy gained by the trolley and mass if there were no frictional forces. If there were no frictional forces, then we hope that the change in gravitational potential energy would equal the gain in kinetic energy. So therefore the simple answer would be 32.5 or 33 joules. Let's see how many of those we got right. So we were right in saying about F equals ma. Substitution and evaluation gave us, so we used the right values, and 6.9. They did say you could use more or fewer decimal places, but significant figures, but try and make that right. The next one poses motion, or to the left, correct, there's only one mark, but any of those. Wheels, trolley, and the bench, the string and the pulley, great. You could also have done air resistance and drag, but I think we covered enough there. We dealt with the GP is mgh. You would have been allowed to have used the 9.81 if you wanted to, but that gave us a figure of, and we were right to put it to 33 joules. To round it appropriately, that would have taken 32.5. Surprised it took 32 there. And then the same number for the last question. So there we go. So actually I didn't take much shorter time than you would have if you did the real exam. That was about 1 hour 30. And only a few errors there, but easy errors to make, so I don't blame you for making some errors, but hopefully that should give you a good overview of the entire paper. Hopefully you did well, and if you didn't, use this video to make sure you don't get it wrong in the real exam. Okay, that's it.